Good afternoon, everybody. First of all, I have to apologize to you. I didn't realize until yesterday that all the grades that you have received this semester were not available to Vista. I usually have my own little program to do that, but I thought that Yaku managed to get the information through Vista. So now it is there, and you can see a list of all of your grades and the course average, including the bonus, so that you know whether you have an A or not for the final exam. An A going into the final exam means 91%. What else? Yeah, so I put on the material for the final exam, and I added the new material, and also I added a notation. I was looking to see if I left out any methods that you may want to study, but I didn't find much. So let's first go over the new material. The transient sensitivity didn't appear in the second interim exam, so that's the only material from the textbook which is in this additional material. And so then we have the material on uncertainty, which are sources of uncertainty, measures of uncertainty, alternative for calculating probability, and measures of safety. And again, one of the bonus problems will appear on the exam. And then I put in annotations for different approximations. For example, I said, why use one approximation over another? This was a problem in the test that people didn't pay attention to the concept of improvement ratio. I added the complex variable approach, and I also added the computational differentiation and advantages of different alternatives. In the topology optimization, I put in the same things that appeared on the exam. From chapter 3, the issues of non-dimensionalization and the relationship between the primal and dual solution. For example, that the dual is the primal is the dual of the dual. That is, the x's are the Lagrange multipliers of the constraints appearing in the dual formulations. I think that that's about it. So what I'm expecting to use the next few minutes is to deal with any questions that you have on the material or on the exam. Yes?
I'm assuming that the time of the exam is 7:30 a.m., not p.m.
Oh, yeah. I didn't put, did I make a mistake or didn't I simply specify?
You didn't specify.
Oh, okay, yeah. Well, I just picked it up from the exam schedule. Yes, actually, I probably would have liked it better if it was 7:30 p.m. Other questions? Yes.
Grading. So whatever points we have now will be scaled down to 65 points, and then the final will be plus 35, or?
Well, actually, it's going to be a bit more in your favor in that the bonus points are not scaled down.
Okay.
So you take your grade without the bonus point, it's going to be, well, actually, even that is not, yeah, I'm sorry, that is true. That is, you take your grade without the bonus point, multiply it by 0.65, take your exam grade times 0.35 and add the bonus points. So it's a bit better than...
So if we have above the A grade, then we can answer only the questions pertaining to the syllabus that has not been covered.
Right, only this material here.
And we get the full time for it.
Yeah. Yeah. I try to put in a strong incentive to do well during the semester, and this is part of it. Other questions? That is, you have the options of doing the other problems too. And for example, if you are completely at a loss how to do the new problems, it may be to your advantage to do some of the old ones. Or you can have a less extreme case where the old problems are easier than the new one, even if you are not completely lost. In terms of time, I'm hoping to avoid the time crunch. We have more than twice the time, that is 120 minutes compared to 50 before. So I'm aiming to increase the time over a midterm by about 50% instead of by 140% or so. So that hopefully you will not have to work feverishly until the last minute. Other questions? I'll give you a couple of more minutes to think about questions before we adjourn. Yes.
Could you once again describe for us the form, the method forms?
Okay. It's easiest to think of the form method if the original variables are normal variables and have a mean value of 0 and the standard deviation of 1. So the first step in the form method is to transform the variable into that shape, by variable transformation that you can find in many textbooks. I didn't give it since we didn't get into the details. But once you have that, you basically have, let's say, if you have only two normal random variable R1 and R2, then you have the limit state function. And this is, let's say, failure. Sorry, the other way around. This is failure. The origin is the place where the random variable are at their mean value, because we assume that they are normal variable with a 0 mean and a standard deviation of 1. And the point which is closest to the origin, in this case it will be this point, is called the most probable point. And we linearize the limit state function about that point, and then you can show that this distance is the reliability index. Which is essentially the number of standard deviation of the limit state that are away from failure. So if the reliability index is 3, it means failure occurs when the limit state is 3 standard deviation from its mean value. 6 sigma would mean 6 standard deviation. So this is essentially the procedure of form. And so the computational cost is simply to find this point. So this is sort of an unconstrained optimization problem where you look on the limit state, where is the point which is closest to the origin. Once you found it, the distance to the origin gives you the probability of failure. So that's what makes it inexpensive. Now, I don't expect you to know all of those details, but just the basics of that is. I'll certainly not give you a problem to go and calculate the probability of failure using form.
So it's cheap because the only computational cost is to find the most probable point.
Right. Well, there is some minor computational cost, which is the transformation of the random variables to the normal, to a standard normal variables. But it is an approximation. The same way that the Monte Carlo method is an approximation. Form is exact when the variables are really normal and when the limit state is linear. Under all other circumstances, it's only an approximation. There is, form stands for first order reliability method. There is also a second order reliability method that takes into account the curvature here. But doesn't change much. It just makes it a bit more complicated and a little bit more costly, a little bit more accurate. Other questions? Yes.
When you say in two example or the bonus problems, you have let x be a standard normal variable n parentheses 0, 1, and then a response n parentheses 10, 1. I'm not sure what those notations mean. Okay. Capital N parentheses.
Oh, okay.
0, 1.
This is a standard notation for a normal variable, and the first number in the parentheses is the mean, and the second number is the standard deviation.
Now, when you say u 0, 1, that means the range of variables can range from 0 to 1.
Yeah. So this is a uniform variable that ranges from 0 to 1. Other questions? Yes.
About safety factor.
About what?
The safety factor.
Safety factor.
The safety factor. When we give the safety factor, let's say like 50%. So we increase the response more than we expect, right?
Yeah, that is the way I define the safety factor. It's the ratio between the response, the capacity and the response. If you design for a safety factor of 1.5, it basically means you multiply the response by 1.5 and you see whether it can be handled by the capacity. In aeronautical application, it's a little bit different in that you multiply the loads by 1.5 rather than the stresses. If you use linear analysis, it doesn't matter, but if you use nonlinear analysis, it can matter. In general, most people think of safety factor as the ratio between the capacity and the response.
So that means we're going to have the probability of failure. We have more chances to have the failure, right?
More chances than what? More than what?
More than normal. If let's say we don't have the safety factor, we didn't say that. Okay, we have response states and capacity states.
Yeah, so in that case, if you design so that the capacity is equal to the response, you'll have 50% chance of failure because you're basically making the mean value of the response equal to the mean value of the capacity. With a safety factor of 1.5, you say the mean value of the capacity needs to be 1.5 times the mean value of the response, and therefore the probability of failure goes below 50%. So for example, if your stresses are 50, you will pick a material that can carry 75. Or if your capacity, that is the ultimate stress that you can handle, is 100, you will design that the stresses will be below 66. That's the meaning of a safety factor of 1.5. Did I answer your question? Okay. Anybody?
When you say accuracy and probability estimates, do you mean the standard deviation and probability of failure?
Yeah, that is what you get out of the Monte Carlo is not accurate, and one way of measuring it is through this standard deviation between repeated Monte Carlo simulations. That is, if you did the Monte Carlo simulation 100 times, this would be about the standard deviation of the different numbers that you'll get from those different Monte Carlos. Other questions? Okay, so good luck on the exam, and that will be all for today.